Hi students, in this section we will deal with techniques to find the unit digit of a multiplication expression and problems related to that. Now, before we go on with the techniques, let's quickly take a side note to understand some basic principles. Say you are doing a multiplication problem. Say for example you want to multiply 13 with 12. All right, now let's do this multiplication, and after we do it we'll derive some insights into the process of multiplication. All right, so I start with multiplying 2 with 3 and 2 with 1, right? So I get 26 over here, right? And similarly I multiply 1 with 3 and then 1 with 1, so that gives me 13 over here, and the answer to this multiplication is 156. All right, now you can note that you got the unit digit 6 in the answer just by multiplying the unit digits in the numbers which you were multiplying. So you can see that over here you have 6 and 3 into 2 is equal to 6. Therefore we can observe that the unit digit depends only on the unit digit. So that's a short way of writing. So basically the unit digit in the answer depends only on the unit digit of the numbers that you are multiplying. Alright, say you have another multiplication. For example, you want to multiply 23 into 76 into 94. You will get a big answer over here, but we are only interested in the unit digit of the answer. Now, to get what comes over here, we don't actually need to do this multiplication. We just need to multiply the unit digits involved, because the unit digit of the answer depends only on the unit digit of the numbers that we are multiplying. So what are the unit digits involved? We have 3 over here, 6 over here, and 4 over here. So if we do 3 into 6 into 4, that gives us 18 into 4. And again, you don't need to take 18, you just take the unit digit of 18, which is 8, and 8 into 4, that gives you 32, and the unit digit of 32 is 2, and that is the digit that will come over here in the answer. So again, the unit digit of the answer depends only on the unit digit of the numbers that we are multiplying. Alright, now an interesting side note over here would be, if you want to find the last 2 digits of a multiplication, that would only depend on the 2 digits of the numbers that you are multiplying. For example, if you want to multiply 1478 and 7293, and say you are interested in finding the last 2 digits of the answer, you actually do not need to do this multiplication. You just need to take the last 2 digits. So over here you have 78 and over here you have 93. So that's 78 into 93, and just by doing this multiplication you will be able to arrive at the last 2 digits of the answer. And remember, the last digit would just depend on 8 and 3. 8 into 3 is 24. The last digit of this multiplication would be 4. We are aware now that the unit digit of a multiplication problem depends only on the unit digit of the numbers that we are multiplying with. Alright, let's move on and learn some interesting concepts about power cycles. Say you want to do 2 to the power 1. That would be just 2, right? Now let's keep increasing the power. Say I want to do 2 to the power 2. That would be 2 into 2, which is equal to 4, right? Similarly, let's do 2 cube. That would be 2 into 2 into 2, and that gives me 8, or it's 4 into 2, right? Because I already have over here 2 square is equal to 4. Now let's do 2 to the power 4. That would be 8 into 2, which is 16. 2 to the power 5 would be 16 into 2, that's 32. 2 to the power 6 is 32 into 2, and that's 64, and 2 to the power 7 is 64 into 2, that's 128. Alright, now in this section we are only interested in the unit digit of these numbers, these solutions we are getting. Let's analyze the unit digit. So I have 2, 4, 8, 6, 2, 4, 8, right? So you can see that the unit digit is repeating, right? I had 2 over here, I have 4 over here, 8, and then 6. Again I get 2, the same number which I had over here. Again I get 4, which is what I had over here. Again I get 8, which is what I have over here. Now if you do 2 to the power 8, you will get 256. Again that's 6, and this is 6 that you have over here. So you can see that as you keep increasing the powers of 2, it keeps repeating in this pattern: 2486, 2486. So 2 to the power 9 would have a unit digit of 2. Similarly, 2 to the power 10 will have a unit digit of 4. 2 to the power 11 will have a unit digit of 8, and 2 to the power 12 will have a unit digit of 6. Alright, now let's try to analyze this same pattern for all the digits from 0 to 9. Alright, so we have all the digits from 0 to 9 over here, and for the number 2, we have just seen that the unit digit when you raise 2 to different powers will either be 2, 4, 8 or 6, and it keeps repeating in this pattern, right? Now 0 for any power of 0, 0 to the power 1 is 0, 0 to the power 2 is 0, so it's just 0. And the same thing holds true for 1. 1 to the power 1 is 1, 1 to the power 2 is 1, 1 to the power 3 is 1. So over here we always have 0 itself, over here we always have 1 itself. Now let's try the same for 3. 3 to the power 1 will give me 3, right? 3 to the power 2 is 3 into 3, which will give me 9. Now 3 to the power 3 will be 9 into 3. The unit digit will be 7, right? Remember, unit digit depends only on unit digit. I know it's 27, but as I'm only interested in the unit digit, I just write the unit digit over here by multiplying 9 with 3, which is 27, and my unit digit over here is 7. Now when I take 3 to the power 4, I will get the unit digit by multiplying 7 with 3, right? I'm only interested in the unit digits. 7 into 3 is 21, so I just write 1 over here, which is the unit digit. Now if I do take 3 to the power 5, that would be 1 into 3, where I get 3 again. So you can see that for the case of 3, the unit digits follow the pattern 3, 9, 7 and 1, and that gets repeated in a similar manner. Alright, now next let's try to analyze the pattern for 4. Let me make some space over here. Okay, so in the case of 4, 4 to the power 1 gives me 4, 4 to the power 2 is 4 into 4. The unit digit over here would be 6, right? 4 into 4 is 16, but I'm only interested in the unit digit. Now in the case of 4 cube, that would be 4 into 6, that's 24, so the unit digit is 4. 4 to the power 4, that's 4 into 4, it's 16. So you can see that the pattern is 4 6 4 6 in the case of 4. Similarly, in the case of 5, you will see that it's always 5, right? 5 to the power 1 is 5. 5 to the power 2, the unit digit will be 5, it's 25. We are only writing the unit digit, that would be again 5. 5 to the power 3 again will have a unit digit of 5. So the pattern in case of 5 is just 5. It will always be 5. Now in the case of 6, it's similar to 5. 6 to the power 1 is 6. 6 to the power 2 will give me 36, but I'm only interested in the unit digit. Now 6 to the power 3 will again be 6 into 6, that's 36, so the unit digit will be 6. So in the case of 6 also, the unit digit will always be 6 if I take powers of 6. Alright, in the case of 7, let's make some space and let's analyze the case of 7. Alright, if I take 7 to the power 1, I get 7. 7 to the power 2, that's 49, but I'm only interested in the unit digit, so I write 9 over here. 7 to the power 3, if I want a unit digit, I have to multiply 7 with 9, that's 63. So I just write 3 over here, which will be the unit digit involved. And in the case of 7 to the power 4, I have to do 7 into 3, that's 21. Therefore the unit digit is 1. And if I take 7 to the power 5, I'll again get 7. So you can see that in the case of 7, the pattern is 7, 9, 3, 1, and that repeats. And in the case of 8, you can see 8 to the power 1 is 8. 8 to the power 2 is 64. I just write 4 because I'm only interested in the unit digit. 8 to the power 3 will have a unit digit of 2, right? Because 8 into 4 is 32. So I just write 2, and 8 to the power 4 will have a unit digit of 6 because 8 into 2 is 16. Now 8 to the power 5 will again be 48. So it will again be ending with 8. So it's repeating. So the pattern in the case of 8 is 8, 4, 2, 6. Alright. Now in the case of 9, 9 to the power 1 is 9. 9 to the power 2 is 81. So I just write 1 in the unit digit. 9 to the power 3 again will have 9 in the unit digit. So 9 and 1 gets repeated. So that's the pattern in the case of 9. Alright. So we have found these different patterns when these digits are raised to different powers. Let me make some space. It's interesting to observe what frequency each of these repetitions have in the case of each of these numbers, and we'll use this property soon. You'll see in different types of problems to find the unit digit, and in problems where finding the unit digit is helpful. Alright, let me make a table over here and let me identify the frequency. In the case of 0, 1, 5 and 6, you can see that the number always repeats, right? And the frequency therefore is 1. It's just 0, 1, 5 and 6. Alright, in the case of 2, 3, 7 and 8, you can see that there are 4 numbers, right? In the case of 2 also you have 4. In the case of 3 also you have 4 numbers. So before you find the first number repeating again. So in the case of 2, 3, 7, 8, I can say that the frequency is 4. Alright, now we are just left with 4 and 9, and you can see that in these two cases the frequency is 2. Alright, having established this, let's keep this aside. Alright, we have it over here, and let's try to apply this in a question. Say you want to find the unit digit of 7 to the power 81. How can we approach this question? So we have to find 7 to the power 81. We have to just find the unit digit of this expression. Now we know that in the case of 7, the pattern is 7931, the pattern of unit digits, right? The pattern of unit digits. Now the answer of 7 to the power 81, when you find the unit digit of 7 to the power 81, will be one of these 4, right? Now let's check in which category 81 belongs to. If I check 81, I can see that 81 is of the form 4k plus 1. Now why do I take 4 over here? Because the frequency for 7 is 4. So I have to find whether the power is of the form 4k plus 1, 4k plus 2, 4k plus 3 or 4k plus 4, which is the same as 4k. So only one of these 4 categories will this power belong to, and to identify that I just need to divide 81 by 4 and take the remainder. When I do 81 by 4, I'll get the quotient as 20 and the remainder is 1. Therefore, I know that 81 is of the form 4k plus 1, and because 81 is of the form 4k plus 1, I can conclude that the unit digit will be 7, right? How do we get that? Let's write the different possibilities over here. You have 7, 9, 3 and 1. If the power would have been of the form 4k plus 1, your answer is 7, right? If it is of the form 4k plus 2, your answer would be 9. If it's of the form 4k plus 3, your answer will be 3. And if it's of the form 4k plus 4, which is the same as 4k, your answer would be 1. Now we have seen that 81 is of the form 4k plus 1. Therefore, the unit digit of 7 to the power 81 is equal to 7. Let's try to do this question. Find the unit digit of 7 to the power 89. Alright, pause this video, give it a try, and then we'll do it together. Alright, we know that for 7, the pattern of unit digits is 7, 9, 3 and 1, right? And you don't need to by heart this, right? All you need to do is, you know, it starts with 7 because 7 to the power 1 is 7. and then 7 multiplied with 7 is 49. So you just write 9 over here, that's the unit digit, and then 9 into 7 gives 63. So you just write 3 over here because that's the unit digit, and 3 into 7 is 21. So you just write 1 over here, the unit digit. 1 into 7 is 7. So it's again starting to repeat and you stop over here, right? So the pattern for powers of 7 in case of unit digit is 7931, and we see that the frequency is 4. All right. Now the power involved over here is 89. Therefore, you have to write 89 in the form 4k plus a remainder. So let's try. 89 divided by 4 will give you a remainder of 1, because we know 88 is divisible by 4. Therefore, 89 has to be of the form 4k plus 1. So 89 can be written as 4 into 22 plus 1, and we have seen it's of the form 4k plus 1. Alright, now whenever the power is of the form 4k plus 1, your unit digit will be 7, right? If k is 0, this is just 1, and that's 7, right? If k is 1, it would be 4 plus 1, that's 5. So in case of 7 to the power 5, you will have a unit digit of 7, and so on and so forth. In the case of the power being in the form 4k plus 2, your answer would be 9, and similarly 4k plus 3 will give you a unit digit as 3, and 4k plus 4, which is the same as 4k dash, it will give you the unit digit as 1. Now we have seen over here 89 is of the form 4k plus 1. Therefore, for 7 to the power 89, the unit digit is 7. Let's do this problem. Find the remainder when 7 to the power 89 is divided by 2 or 5 or 10. Alright, now there is a hint given in the bracket. So this is just for our practice. In the real exam questions, you won't get a hint. But dividing by 2, 5 or 10 depends only on the unit digit. Now pause the video, give it a try, and then we'll solve it together. Alright, we are back. I hope you have given it a try. Say you have a number ABC, and A, B or C can be any digit. Alright, the expanded form of a 3-digit number like this is A into 100 plus B into 10 plus C, right? For example, if you have 217, you can write it as 2 into 100 plus 1 into 10 plus 7 into 1. Alright, now you can see that in this case 100 and 10 is divisible by 2 or 5 or 10, right? 100 is perfectly divisible by 2, 5 and 10, and 10 is also divisible by 2, 5 and 10. So when you do a division by 2, 5 and 10, that's why we say that the remainder will depend only on the unit digit. Now what do I mean with that? Let's take an example. Say you want to do ABC divided by 2 and you want to find the remainder. Now I can write ABC in the expanded form as A into 100 plus B into 10 plus C, and I need to divide that by 2 and get the remainder. Over here you can notice that this is equal to C by 2 and taking the remainder, because A into 100 by 2 will give you a 0 remainder because it's perfectly divisible. B into 10 by 2 also will give you 0 remainder because it's perfectly divisible. So the remainder will only depend on the unit digit, which is C. Alright, having established this, let's keep it aside and let's come to the question. The question says 77 to the power 89 divided by 2, what's the remainder? We have seen that this will only depend on the unit digit, and we have seen in a previous section that 7 has the power cycle 7, 9, 3, 1, right? And 89 is of the form 4k plus 1. So when the power is of the form 4k plus 1, the unit digit will be 7. So this expression can be written as 7 by 2, finding the remainder of 7 by 2, because the unit digit of 7 to the power 89 is 7. Now 7 by 2, if you want to find the remainder, that's 1, because 7 is 3 into 2 plus 1. So your answer over here is 1. Now similarly, 7 to the power 89 by 5 remainder would be equal to 7 by 5 remainder, right? The same logic is applied. 7 to the power 89 will have a unit digit of 7. That's why we write it as 7 by 5 remainder, and 7 divided by 5, if you do that, you'll get a remainder of 2, because 7 is equal to 5 into 1 plus 2. Similarly, 7 to the power 89 by 10 will give you a remainder of 7 itself, because that's 7 by 10, right? You do 7 by 10 remainder, you get the answer as 7. It goes 0 times. So 7 is equal to 0 into 10 plus 7, and 7 itself is the remainder. Let's do this question. The sum of the third powers of the first 100 natural numbers will have unit digit of what? Alright, so pause the video, give it a try, identify the unit digit when you do 1 cube plus 2 cube up to 100 cube. Alright, we are back. I hope you have given it a try. Let's try to do it together. Alright, so let me take the first 10 natural numbers. That's 1 cube plus 2 cube up to 10 cube, right? Now let me take the next 10 natural numbers. That's 11 cube plus 12 cube up to 20 cube. Alright, now let me analyze these two sets. So I have one set over here and one set over here. And remember, we are only interested in the unit digit. Alright, what can we observe about the unit digit in both these cases? You can see that both of these will have the same unit digit when you do the addition, right? Why? Over here you have 1, 2, 3 up to 9 and 0, right? So unit digit depends only on unit digit. So 1 cube will give you 1 in the unit digit. Similarly, 2 cube will give you 8 in the unit digit. 3 cube will give you 7 in the unit digit, and so on and so forth. The same thing you can notice over here. The unit digit depends only on the unit digit. So 11 cube will have also 1 in the unit digit. 12 cube also will have 8 in the unit digit, because the unit digit depends only on the unit digit. Similarly, 13 cube will have 7 in the unit digit. So you can see that the unit digits that we have over here and the unit digits that we have over here, when we do the addition, it's the same. Therefore, this expression over here and this expression over here will have the same unit digit. Let's take that as x. Alright, now you can see that when you do 1 cube plus 2 cube up to 100 cube, you're actually getting a unit digit of 10x, right? 10x, because you have this type of expressions 10 times. One is 1 cube to 10 cube, right? Similarly, you have 11 cube to 20 cube, you have 21 cube to 30 cube, and it goes on till 91 cube to 100 cube, right? This you can notice there are 10 such sets. So over here you have 1, over here you have 2, and over here you have 9. So you count from 1 to 9, that's 9, and this is over here, it's equivalent to having 0. So 0 to 9, that's 10 such sets, and each of these will have x in the unit digit. So when you find all these numbers and you add them up, it's equivalent to doing x plus x plus x 10 times, that's 10x, and 10 into any number, whether x is 1 or 2 or 3, right? When you do 10x, the unit digit becomes 0, right? Because 2, for example, if x is 2, 2 into 10 gives you 20. You can see that again the unit digit is 0, right? Therefore, the answer of this is 0, right? The unit digit will be 0. Now, over here, you have seen that the third powers, when we added, we have got the answer as 0. Now, you can, by this same logic, you can see that instead of third power, if it was given any power, the answer would have been 0, right? Imagine the question was that the sum of the fifth powers of the first 100 natural numbers will have a unit digit of. So the same logic applies. 1 to the power 5 up to 10 to the power 5. If you add that, and if you add 11 to the power 5 up to 20 to the power 5, both the cases will have the same unit digit, and you'll have 10 such cases. Therefore, for the sum of any power of the first 100 natural numbers will have a unit digit of 0. All the powers have to be 0. So like 1 cube to 100 cube will have a unit digit of 0. Similarly, 1 to the power 5 up to, you add up to 100 to the power 5, also you will get a unit digit of 0. Or 1 to the power 7 or 1 to the power 6 up to 100 to the power 6. In all these cases, in the case of any power, your unit digit will be 0. Let's do this question. Find the rightmost non-zero digit in 2340 to the power 892 plus 340 to the power 936. Pause the video, give it a try on your own, and then let's solve it together. Alright, we are back. So the question that we are trying to solve is 2340 to the power 892 plus 340 to the power 936. Let's analyze the exponents in these two numbers. So over here you have 892 and over here you have 936. We can see that 936 is greater than 892 and we are trying to find the rightmost non-zero digit. Therefore we can ignore the number with the greater power because it will have more zeros, right? What do I mean with that? Say you take 20 to the power 3, right? That's equivalent to 2 to the power 3 into 10 to the power 3, right? And you can see that this results in 3 zeros. So you'll have 2 to the power 3 is 8 and you have 3 zeros. Now if I have another number, say 10 to the power 5, you can see that over here I have 5 zeros. So let me write that so that we can visualize it. So I have 3, 4, 5. I have 5 zeros. And if I add that, you can see that suppose the question was 20 cube plus 10 to the power 5. What is the rightmost non-zero digit? So 10 to the power 5 does not matter, right? You can see it's zeros. So even if I ignore this, I will get still the same answer, that's 8. So in this case, if I add them, the answer has to be 8, right? So over here, because the power is greater, you can see 5 is greater than 3, so it has more zeros. So in this type of a question, you can ignore this one and you just need to find 2 to the power 3. Over here you can ignore the 0 and this translates to 2 to the power 3, which is 8. That's the answer we are getting over here. Let's apply the same logic in this question. Let me make some space. We have seen that 936 is greater than 892. Therefore I can ignore this number over here because it has more zeros, right? And I'm trying to find the rightmost non-zero digit. Alright, let's move on. So over here I have to only take 4 to the power 892 to get the rightmost non-zero digit, right? 0, this would be 234 into 10. I can split this as 234 into 10 to the power 892, right? So this part over here, 10 to the power 892 will give me a number with 892 zeros, but I'm not interested in that because I need to find the non-zero digit, the rightmost. So I just need to find the unit digit of this expression. So unit digit depends only on the unit digit. So whether I take 234 to the power 892 or 4 to the power 892, both will have the same unit digit, right? So I just need to find the unit digit of 4 to the power 892, and we know the frequency for 4 is 2 because 4 to the power 1 is 4 and 4 to the power 2 is 6, and again it repeats as 4646, right, like that. So the frequency is 2. So we need to write 892 either as 2k or 2k plus 1, right? So we can see that 892 is divisible by 2, right? It's a even number. Therefore 892 is of the form 2k, and therefore I can say that the unit digit of 4 to the power 892 is equal to 6, right? The frequency is 4 and 6. So if you have 2k plus 1, the unit digit would be 4, and if you have 2k plus 2, or that's the same as 2k dash, you will have your unit digit as 6 because 892 is of the form 2k. Therefore 4 to the power 892 will have 6 in its unit digit.